Section 5.1 is on operations with polynomials. A lot of these rules that we're going to go over you'll probably remember from Algebra 1. The first is the product of powers. If I have x to the a power times x to the b power, I add the exponents. An example of this is x squared times x to the third equals x to the fifth. Quotient of powers. X to the a power divided by x to the b power equals x to the a minus b power. Or an example, x to the seventh divided by x to the third is x to the fourth, because 7 minus 3 is 4. Negative exponents. X to the negative a power is the same as 1 over x to the positive a. 1 over x to the negative a is the same as x to the power of positive a. An example of this, x to the negative 7 is 1 over x to the positive 7, and 1 over x to the negative 7 is x to the positive 7th. The rule is, the way I look at it is, you can move the whole power over the fraction bar and make the exponent positive. So here we have a negative exponent basically on the top. I can move it to the bottom and make it positive. Here I have a negative exponent on the bottom. I can move it to the top and make it positive. And the last property we're going to take a look at here is the power of a power. X to the a, the whole thing raised to the power of b, you multiply the exponents. So x to the third, whole thing raised to the fourth power, is x to the 12th. Oh, wait, we do have a few more rules here. Power of a product. So if I have two things being multiplied, like x times y, and that is raised to the power of a, that's the same as x to the power of a times y to the power of a. So 3x, the whole quantity raised to the fourth power, is 3 to the fourth power times x to the fourth power, or 81 x to the fourth. Power of a quotient, same idea. X divided by y, all raised to the a power, is x to the a divided by y to the a. An example of this is 5/6 squared is the same thing as 5 squared over 6 squared, or 25 over 36. And if you have a quotient raised to a negative power, it's the same as flipping or multiplying by the reciprocal of that quotient. So x divided by y raised to the power of negative a is the same as y divided by x raised to the power of positive a. Here's an example. 3/4 to the negative third power is the same as 4/3 to the positive third power. And then you would raise 4 to the third power, which is 64, and 3 to the third power is 27. And don't forget that anything raised to the power of 0 is equal to 1. 8 to the 0 power is equal to 1. So how do you know if you're done simplifying a monomial? It's completely simplified if there are no powers of powers, that is, no parentheses, no exponent inside the parentheses and an exponent outside the parentheses. Also, each base appears only once. Your answer has only one x, one y, one a, one b. All fractions are in their simplest form, and there are no negative exponents. So let's take a look at a couple examples here. We need to simplify each expression. For number 1, we have 5x cubed y to the negative fifth times 4xy cubed. So the first thing I'm going to do is work on my coefficients. 5 times 4 is 20. And I'll have x to the third times x to the, that's basically a 1. That's going to give me an x to the fourth. And then y to the negative fifth times y to the third. I add those. That gives me a y to the negative 2. Negative 5 plus 3 is a negative 2. But I can't have a negative exponent, so I can keep my 20 x to the fourth on top, and I can move my y squared to the denominator. And that's simplified. Let's take a look at number 2 here. I'm going to deal with this kind of as 4 different problems. I'm going to deal with my coefficients, my x's, my y's, and my z's. So negative 7 over 21 is the same as negative 1/3, dividing top and bottom by 7. X to the fifth divided by x to the seventh is x to the negative 2, because 5 minus 7 is negative 2. Y to the fifth times y to the fifth, subtract, that gives me y to the 0. And then x to the fourth, z to the fourth times z divided by z squared gives me a z squared. Now let's clean that up a little bit. First of all, y to the 0 is just 1, so I don't need to worry about that. This x to the negative 2 needs to go on the bottom as an x squared. So I'll have a 3x squared on the bottom, because the 3 of this 1/3 is on the bottom, and a z squared on top, and a negative out front, and that's simplified. Number 3, n to the 5th, the whole thing to the 4th power. Remember, multiply your exponents, n to the 20th. So the definition of a polynomial is the sum or difference of monomials, and what we've been looking at so far are all considered monomials. So it's going to have addition or subtraction in it. There are no negative exponents or variables in the denominator, and there's no roots, no square roots, no cube roots, anything like that. The degree of a monomial is the sum of its exponents. So just add up the exponents of each monomial. The degree of the whole polynomial is the degree of the monomial that has the greatest degree. Let's take a look at a couple examples. Determine whether each expression is a polynomial, and if it is, state its degree. So for number 1, we have x to the 4th minus 4 times the square root of x plus 18. This is not a polynomial because it has a square root. No square roots in a polynomial. Because actually, as we'll see in a later chapter, that's x to the 1/2 power, and you can't have rational powers. Number 2, negative 16a to the 5th plus 3/4 a squared b to the 7th. This does have a fraction, but that's okay. So this is indeed a polynomial. So yes. Now we need to find its degree. Let's look at the degree of each monomial. So here's one monomial, and here's another. The degree of this monomial is 5 because it only has an a raised to the 5th power. The degree of this monomial is going to be 9 because I have an a squared and a b to the 7th. Remember, it's the sum of the exponents. So the degree of the whole polynomial is the greatest degree of any monomial. So that's going to be, that's going to be 9. So my degree is 9. And number 3 here, I have x squared minus 3x to the negative 1 plus 7. And no, this is not a monomial because it has a negative exponent. Remember, what that negative exponent would do is put that x in the denominator, and you cannot have a variable in the denominator of a polynomial. Now, to add or subtract polynomials, we're just going to combine like terms. To multiply polynomials, use the distributive property. So number 1 here says simplify 2x to the 3rd plus 5x minus 7 minus the whole polynomial x cubed, or x to the 3rd minus 3x plus 2. Now, remember, this negative sign means that I have to subtract each one of these terms. Or another way to think of it is I'm going to multiply each term in my second polynomial by a negative 1. So let's just copy the first one without parentheses. And then let's multiply each one of these by a negative 1. Negative x cubed plus 3x minus 2. Now it's just a matter of simply combining like terms. So 2x cubed minus x cubed is going to give me a 1x cubed. 5x plus 3x is 8x. And negative 7 minus 2 is a negative 9. Subtraction is a little tricky. Make sure that you subtract each term of the second polynomial. In our last example here, I have 5xy times the quantity 2x minus y plus 6y squared times the quantity x plus 6. First thing I want to do is distribute. So 5xy times 2x is going to give me 10x squared y. 5xy times negative y is going to give me negative 5xy squared. Distributing 6y squared times multiplied by x is going to give me 6xy squared, and then 36y squared. It doesn't matter what order you put your variables in, but generally we put them in alphabetical order. Now I want to look and see if I have any like terms here. Remember, those are going to be terms that have exactly the same variables raised to exactly the same powers. So here I have an x squared y, and I don't have any more of those. Here I have an xy squared and another xy squared, so those are like terms I can combine, and only a y squared there. So I'll have 10x squared y plus xy squared plus 36y squared, and that is simplified. Now, just a reminder, what we talked about in this section was operations with polynomials. We reviewed a lot of the rules regarding exponents and powers that we learned in Algebra 1 and applied those to examples. We also talked about degrees of both monomials and polynomials.